All right, so for question number 2, okay, we're looking to describe each of the following scientists' invention, okay, the type of energy the inventor was able to produce, and how it was produced. Okay, so what did Ørsted produce?
But there was an electrical current in the wire, or the electrical current could produce magnetic effects.
Right, okay, he produced magnetic energy essentially from electrical energy with his current carrying wire and compass apparatus. Okay, what about Faraday?
Electric energy?
Right, he made electric energy from magnetism. He did the exact opposite. He made the coil of wire, pushed the magnet through it, the magnetic field pushed the electron through the wire, okay, forcing a current to flow. All right, what about Seebeck?
Heat energy?
He used heat to make,
Electric.
oh, right, he made the first thermocouple, okay, so he was the one who did that. And then Edison, we didn't really talk about him, but he was in there. What did Edison do? Sometimes when you have a good idea, we imagine one of these over your head. Light bulb, yeah, Thomas Edison invented the light bulb, which turned electrical energy into heat and light. Okay, the tungsten filament light bulb that I was talking about yesterday. Okay, Edison is famous for being interviewed and having a person ask him, "You failed so many times, like nearly 1,000 times to build a light bulb. Did you ever consider yourself a failure?" He said, "Nope, I found out 1,000 ways how not to build a light bulb." Okay, so he's totally a glass half full kind of guy. All right, and then Volta. What did Volta do? He made the first battery, which turned chemical energy into electrical energy. Okay, for each of the inventions identified in question 2, state a practical use of the invention today. All right, turning electricity into magnetism would be an electromagnet. Okay, we also kind of use that for electric motors. Okay, they have an electric current that flows through them that alternates magnets and turns the motor. Okay, Faraday, generator. Okay, Seebeck, we talked about how that's used in the brake rotors of electric cars or in circuit breakers in your home. Okay. While Edison did invent the light bulb, we don't use the tungsten filament light bulb too much anymore. Okay, but practically it still would serve the same purpose, shedding light and darkness. Okay, and for Volta, well, we still use chemical energy to power electric devices via batteries. All right, for number 4, what's the difference between nuclear fusion and nuclear fission?
Fission is when the atom splits in half, and fusion is when two join.
Right. Okay. Fusion means to push 2 together to make 1, and fission means to split 1 into 2. Okay. How are they similar? They both release the energy stored in the nucleus of the atom. Okay. All right. For number 6, what is the modern theory of the source of energy from the sun? It's a big what?
Like nuclear reaction, because
Yeah.
the gravity's pushing the cells together.
Right. The atoms together.
Yeah, the atoms and then.
Yeah, exactly. Nuclear fusion, okay, is the fuel that drives the sun. Gravity pushes the hydrogen atoms together to make helium, and that process will continue to go on for probably another 3 to 4 billion years. Okay, so it's nothing we'll have to worry about. But at that point, the sun will begin to run out of hydrogen fuel, and it will begin to fuse helium into larger atoms. And at that point, it'll pretty much fail, and then it will swell up and become a red giant, which will swallow the Earth. And then it will cool down and become a little white dwarf. We'll be gone by then. Okay. All right. Number 9, describe the contributions of the people here. So Sadi Carnot, what did he do? He was right before Joule.
He discovered that heat could be converted into mechanical energy when the thermal energy flows from hot to cold.
Exactly. And he took that whole idea that energy flows from hot to cold, and he said if you put something in the middle, you'd be able to make it work. Turning heat into mechanical energy. Basically came up with the idea for the heat engine. Okay, what about young? Right here, Thomas Young linked mechanical energy to this idea of kinetic and potential energy in moving objects. He defined energy, okay, as the ability to do work. That was Young's contribution. I think Black is the next one, right? Okay, so Black came up with this idea of thermodynamics, that energy flows from hot to cold or high to low. Okay, came up with this caloric fluid idea that, you know, at least explained the flow, if not the practical way that energy moves. Okay, and then I think Thomson was the one after that. Okay, and he's the one who discovered the link between mechanical energy and heat, and that you could convert mechanical energy into heat. Okay, while making cannons and having coffee breaks. All right. So Joule proved that heat could be produced from potential energy with his falling block apparatus. Okay. So we need to explain how that worked. Well, when I move the falling block up and away, what have I done? I've given it potential energy. I've done work, transferred mechanical energy to the falling block. When I let it go, gravity will convert the gravitational potential energy into kinetic energy, causing the falling block to slam into the stationary block, at which point the mechanical energy, which is all kinetic at that point, will be turned into sound and heat. Okay? And that's where that comes from. Okay, for number 12, in the following situations, identify the major form of energy involved. Okay, an antacid tablet is placed in a glass of water and plop, plop, fizz, fizz. What kind of energy is that? It's chemical. Yeah, that's a chemical reaction. Okay. All right, a fluorescent dial on a wristwatch glows at night. It glows because it's making light. Yeah, it's just light energy. Okay, that's all it is, light energy. Okay, downhill skier begins to ski down the slope with increasing speed. Two answers for this one. I would say kinetic would be good, yes. Okay, potential would be also true at the top of the hill. Let's say three possible answers then. What do those two things make up? Mechanical energy. I would say if this was a multiple choice question, the most correct answer would be mechanical energy, because it includes both potential and kinetic. Okay, that's why every multiple choice test always says choose the best answer, never the correct answer. There can be more than one correct answer, but there is never more than one best answer. Okay. All right. A tingling sensation is felt on the tongue when it is touched to the terminals of a 9-volt battery. Any of you ever done this? Yeah. This is how we used to test batteries when I was a kid. Right? We didn't have like fancy batteries. Nothing, everything ran on these things. Okay. Yeah, so if you put your tongue across the positive and negative terminal and the battery was good, you got a bit of a zap. And if it wasn't very good, it like barely tingled. You had to be brave though. Right? You never knew where that battery had been. Okay. All right. E, the inside of a car gets extremely warm if it's left in the sunshine. What kind of energy is that? Starts with T. Thermal energy. Okay. How many people wanted to say heat? Okay. Is heat a form of energy though? No, heat is the transfer of thermal energy. Okay, so heat is actually not a form of energy, it's the transfer of thermal energy. It works just like work does. Work is the transfer of mechanical energy, heat is the transfer of thermal energy. Okay? All right, a seagull lifts a clam high above the beach. Mechanical would be the best answer, but you could also say potential or kinetic, okay, because it would have both. A compass needle points north. Magnetic. Yeah. Okay, for 13, describe an appliance or machine that, for its operation, requires the following forms of energy. Chemical, battery, or anything that runs on gas. okay, would require chemical energy. Light.
Solar panel?
Yeah, anything that's solar powered, anything connected to a solar panel would require light. Okay, heat.
Would a microwave work for that, or would that be
A
more?
microwave would produce heat. What would require heat?
Was it thermocouple?
The thermocouple. Yeah, anything that uses a thermocouple. All right, electrical. We won't even get into this. Anything you plug into the wall or put a battery in. Lots of stuff. Okay, for that answer. And then magnetic. A compass. Okay, and believe it or not, your phone. Because without magnets and electricity, electromagnetic waves, radio, cannot be produced. Okay, so there is magnets in all transmitters and receivers. Okay, number 14, describe an appliance or machine that produces the following forms of energy as it operates. Chemical. A refinery. Okay, anything that refines like crude oil or anything like that would produce chemical energy. Okay, and I know this isn't an appliance or a machine, but a plant would also produce chemical energy. What about light?
A lamp.
A lamp, a light bulb, okay? Even a toaster, okay? I mean, the little elements inside glow, they're emitting light, okay? So that can be true as well. Thermal energy.
Hairdryer.
Microwave, hairdryer, electric heater, okay? Furnace. Electrical energy.
Plugging anything into the solar.
A battery, yeah. Okay, solar panel. Any of those things would produce electricity. And magnetic energy. Phone. Electromagnet. Okay, electric motor. All right, that's it for those. All right, so we talked about this thermodynamic stuff.
So for the chemical, if it was on a gas, could we put one?
Yes, and it would be a multiple choice question, and I probably wouldn't say machine or appliance. I would say which of the following produces chemical energy. Yeah, and then plant would be viable. Okay, so this is what Black came up with, right? Okay, he was talking about the flow of energy, okay, from hot to cold. That's the laws of thermodynamics. So we're going to be looking at the laws of thermodynamics because they govern how basically all things operate. Okay, because in order for anything to change, work is going to have to be done, okay, or heat is going to have to be transferred. So, all machines in daily life are governed by these physical laws. They describe the relationships between work and energy transformations. Okay? However, thermodynamics focuses mostly on heat as a transfer of thermal energy. Okay? Thermodynamics doesn't generally look at mechanical energy. Okay? That's usually mechanics that look at that. Okay? So, we're going to look at any changes in temperature that are also the result of either work being done or energy being transferred or transformed even, okay, as the case may be. So the first thing we need to understand is that there are three kinds of systems, okay? We need to know these three kinds of systems because they tell us whether energy can be exchanged with the environment or not, okay? So a system, okay, a definition of a system is a set of interconnected parts, which is really kind of a misleading definition. A system is any number of things that are interacting energetically, all right? That means that they could do work on each other or transfer heat to each other, okay, whatever, okay, that's a system, okay? If they can be in contact in some way and transfer energy to each other, they are a system, okay? Most of the systems that we deal with are open systems. And in an open system, both matter and energy can be exchanged with the surroundings. Right? So right now, you are an open system. Okay? In this room, okay, which is your surroundings, you are exchanging matter because you're inhaling and exhaling. Okay, so you're exchanging oxygen and carbon dioxide, that's matter. Okay, and you're also exchanging energy. Okay, it's about 20 degrees in here, but it's much colder than that outside. And I don't have the heat on in here. And in fact, I keep it that way most of the time. Even when it's really cold outside, I don't turn the heat on in here because you guys will heat the room. Okay? If I get 25, 30 people in here, 4 classes a day, it can be 26 or 27 degrees in here by the end of the day. So I don't turn the heat on. Okay? You guys exchange energy, thermal energy, with your surroundings as a result of, okay, just being here. On an exam day, it's even worse. Okay? You get the stress sweat going on. Okay? And you get like the anxiety funk in here. But it gets warmer. I kid you not. Okay? Like stress will do that. Okay, so that's an open system. It exchanges matter and energy with its surroundings. Okay? A closed system is airtight, so it cannot exchange matter, but can exchange energy with its surroundings. So this would be, like for example, you go to the grocery store and you buy some food and you put it in a Ziploc bag and put it in the freezer. Okay? Once it's sealed in the Ziploc bag, it can't exchange matter. No water will escape, okay? No gases will get in or out, but energy will escape and eventually the food will freeze. Okay? That means it's losing energy to the fridge, its surroundings. Okay? So that's a closed system. Anything that's airtight and does not exchange matter or energy with its surroundings is a closed system. Okay? The last one is entirely theoretical. You cannot build a perfectly isolated system. Okay? An isolated system cannot exchange matter or energy. Right over there. Okay? Cannot exchange matter or energy with its surroundings. So that means not only is it airtight, it's also completely insulated. No energy gets in or out. And that's what's basically impossible to do. We cannot build something that will not exchange even the smallest amount, okay, of energy with its surroundings.
Would that, sorry, I forgot what I was gonna say. Oh yeah, no, is that what it's like with like coconut milk? Kind of? Like, is air able to get inside the coconut? To, like,
Oh
sweeten
yeah,
the milk?
yeah, there's
Oh, like, yeah.
osmotic exchange
okay.
and yeah, for sure. It's sealed so the coconut milk doesn't get out, but I mean, it's a living thing, right? So stuff is still exchanged through it. All right, so an isolated system is basically impossible. Like I often have people say to me, well, Mr. Coderre, the International Space Station is an isolated system. And I quickly point out that it certainly is not, okay? It exchanges a great deal of energy with its surroundings. When it's on the dark side of the Earth, they have to turn all the heaters on to keep it from freezing. And when it's on the sunny side of the Earth, they have to run the coolers to keep it from overheating. Okay? It exchanges a lot of energy with its surroundings. It's covered in solar panels, so it's constantly taking in energy from the sun. That's an exchange. Okay? And in fact, it also exchanges matter with its surroundings. The space toilet has to go somewhere. Okay? And every once in a while, they jettison the space toilet and make a poop comet. I kid you not. Okay? Every once in a while, they jettison what is in the space toilet and it burns up in the atmosphere. Thankfully, it does not make it all the way to the ground. Okay? Yeah. Right? But Chris Hadfield was telling people about that in an interview, and he's like, yes, the next time you see a beautiful shooting star in the sky, remember, it could just be the poop. Because that's what happens. All right. First law of thermodynamics. Okay, so the first law of thermodynamics is the law of conservation of energy, okay, which is just like the law of conservation of mass. You cannot create energy, you cannot destroy energy. You can convert it from one form to another, you can transfer it from one system or object to another, but you cannot create it or destroy it. Okay? All that ever happens is its transfer or conversion. Okay? And then lots of people will say, well, Mr. Coderre, the sun's creating energy all the time. No, it's not. It's converting the nuclear energy in the hydrogen that it's made up of into light and heat and all the other things. It's not creating energy. Okay? All the energy that ever will be was formed at the Big Bang. Okay? And there will never be more or less energy. Okay? It'll be converted into lower and lower forms and be harder and harder to use, but it will never decrease. Okay? That amount of energy is always fixed. Okay, so the first law goes, no, it's not even stated on that one. Okay, but anyway, the energy of a system can be increased in two ways. Okay, so you can change the energy. We don't necessarily have to say increase. Okay, you can change the energy of a system in two ways: heat and work. All right, if you do work to a system, its energy will go up or down. Up. If I do work, I'm transferring energy to the system. Okay, if heat is transferred to the system, its temperature will go up. Its thermal energy will increase. Okay, but the reverse is also true. If the system does work on something else, it's transferring energy away. Okay, if it transfers heat, it's losing thermal energy to something else. Okay, those are the two ways that the energy of a system can change: heat and work. Right. All right. So, first law of thermodynamics, it's highlighted on there already, but it's super important. Okay, is just a restatement of the law of conservation of energy. Okay. It states that total energy, including heat in a system, remains constant. Okay, and it can be changed, but it can't be created or destroyed. All right. Second law of thermodynamics deals with the direction heat flows. Okay, heat always flows from hot to cold. Okay, that's the second law of thermodynamics. Energy always flows from hot to cold or high to low. Okay, so in this case here, this is not, maybe the smartest thing to do, but putting this piece of metal into hot water. Okay, which direction will the heat go? So this water is really hot. Okay, this metal rod is not. Which way is the heat going to go? Up the rod. Okay, if the rod was really hot and you put it in the water, then it would go the other way. Okay, then the water would heat up. So that's just telling us which direction heat flows. This is why when you're cooking over a stove, like soup or whatever, you don't use a metal spoon. Okay, a metal spoon is a good conductor of heat, and it's always going to be cooler than what you put it in on the stove, so it's naturally going to transfer up the metal handle into your fingers. Okay, if you use a wooden spoon, wood is a good insulator, a poor conductor of heat. Doesn't mean energy is not going to try and flow up the wood, but it doesn't do it as well.
I know this is really unrealistic, but like theoretically, if the bottom of the hole was warm then, and then you had like a bucket of water hanging from the ceiling and you stuck it in like a tiny hole in the bottom, then would the heat flow upwards into the water above you?
Yep.
Okay.
Yeah, heat, remember, heat is energy. It's not matter. It doesn't obey gravity, right? Heat can go whichever way it wants to, and it's always high to low. Okay. All right, and then this is an example of a transfer of mechanical energy. So if you had like a pogo stick, okay, with these like springs or elastic bands on them, okay, you jump up into the air and then you land on the thing and you compress the spring. You're doing work on the spring. So energy is going from the high energy object, you, to the spring, okay, and then you compress the spring. When you stop, the spring is fully compressed and now it has more energy than you do and it pushes you up. Okay, and so it's always going to go from high to low. Okay. Now, how many people have heard of this? Perpetual motion machine. Okay. What can they supposedly do?
They can move infinitely and provide their own energy.
Right. They can move infinitely and provide their own energy. So if I had a perpetual motion machine and set it in motion, it would never stop. Okay, why is that impossible?
Because you're always going to lose energy in like a sort of sound, heat, or anywhere.
Exactly. Second law of thermodynamics forbids the formation of a perpetual motion machine. Okay, it's always going to lose energy to its surroundings because it's always going to be moving. Okay, so there's going to be sound. If there's sound, that means there's friction. Friction is a place where energy is lost. It'll be transferred to the surroundings and the machine will stop. Okay? The same is also true for this. A perpetual motion machine, even if you could build one, would be nothing more than a scientific curiosity. it would be utterly useless. Because it could never do any work. Because what's work? A transfer of energy. If you don't put energy into the machine and it does work, it'll stop. Okay? Because work is a transfer of energy, and it would lose energy to whatever it did work on, and then it would stop. If it could do work and not stop, then it's violating which law? The first one. It's creating energy. The only way you could do work and not have any energy put in is if you're making it yourself. Okay? Which you can't do.
Okay, let's say we do figure this out and we do break the law. Does that just mean we replace it, or like is that just like universally not okay?
If you manage to do that, remember me.
Okay.
Because you're going to be so rich and powerful.
Okay.
Okay? Yeah. Okay? Yeah. Don't make me like an underling.
Okay.
Give me a good job. I'll still work. But yeah, like there's just no way to do it. You can't get something for nothing. Okay? And a perpetual motion machine is basically always getting something for nothing. It's running, and if it actually did work, then it's doing even more than that. It's creating energy from nothing. Okay? All right. So, second law of thermodynamics describes the direction of energy flow in natural processes. The second law states that heat always flows naturally from hot to cold, but never naturally from cold to hot. Never naturally from cold to hot. Does that mean I can make it go that way? Yes, I can. It's just like active transport. Okay? In biology, we learned that materials, if you use energy, can be pumped up the gradient instead of down. Okay? They flow down the gradient, but they can be pumped up the gradient. The second law of thermodynamics can be circumvented if you're willing to invest energy in it. Okay? This is how your refrigerator works, how your air conditioner works. Okay? They are what we call heat pumps. Okay? And what they do is they use energy and they pump heat from a colder area to a hotter area. Okay? So if you're talking about your refrigerator, okay, next time you go up to your fridge and it's running, feel around the sides and the bottom. What are you going to feel?
It's warm.
It's warm. Okay? It's pumping the heat from the food inside out into the room. But naturally, the energy wants to go from the room into the fridge because that's high to low, hot to cold. Okay? So your fridge has to use energy in order to pump the heat that's in it out into the warmer area. Okay? And in fact, that uses a lot of energy. The appliance in your home that uses more energy than anything else is your fridge. Okay? Because it's running all the time. Okay? And it's going against the second law of thermodynamics. Now, if you have an electric stove, when that's on, it uses more energy than your fridge, but you don't use it all the time. Okay? So your fridge is your largest consumer of electricity. If you have air conditioning, also a big one. Okay? Because it's trying to do the same thing with a much bigger volume of air. Okay? You don't want to try and use your refrigerator as an air conditioner. Okay? Homer Simpson tried this once, and he destroyed his fridge. Okay? Why? Here's what he did. He put a blanket over the fridge and opened the door and sat inside the blanket with the door of the refrigerator open. Why did that destroy the refrigerator?
Because wouldn't all the cold air be leaking out from the fridge, like into the hot air as the hot air is coming into the fridge?
Exactly. What it's trying to do, the fridge is trying to pump the hot air from inside the fridge out into the room. All he's done is make those two places the same place by leaving the door open. Okay? So all the heat from him is going through the condenser and being pumped back into the place where it's supposed to be getting colder. And so it always is working against itself until the compressor just dies. Okay? Well, you shouldn't leave the fridge door open. Okay? If you do, you're trying to air condition your house with your fridge, and the compressor is not designed to do that. It's designed to cool however many cubic feet your fridge is, okay? And not the whole house. Yeah? That's why most fridges have a beeper on them. Okay? Okay, these are a couple of examples of perpetual motion machine ideas that people came up with. okay? This one with the wheel and the little ball bearings, okay? They've got the kind of sections in it, and the idea was that as the wheel turned, the ball bearing would roll over this little hump to this side, and gravity would pull it downwards, which would turn the wheel, and then as it came up this side, it would roll back to the center, where it was easier for the wheel to move, and that the wheel would move continuously. It won't work, because every time a ball moves,
Sound.
there's sound, which is a loss of energy to the surroundings, okay? And so it'll eventually quit. This one had potential, because a magnet is kind of free energy, but it's kind of cheating too, okay? I mean, you're still putting energy into the system, so it's not a perfect system. You have a source of energy in the system constantly, okay? The idea was that these ball bearings would come up the ramp attracted to the magnet, but before they got to the magnet, they fall through this hole and roll back down. But what do they have to do right here? They have to open this door. Is that a transfer of mechanical energy? It's work, okay? So it won't work, because it has to do work, okay? Always gonna have to open that door. All right. Okay, here's the heat engine thing. This is what Sadi Carnot was trying to figure out, okay? So he knew that you could build a heat engine if you had a high temperature area and a low temperature area, and you put your engine between them, because heat would want to flow from high to low, and when it does that, it's going to take matter with it, okay? And the matter can then do work. All right, so what would happen is you'd have this engine here, it would do some work, and the rest of the energy would continue on to the low temperature area, okay? Perfectly sound idea. His way with the two pipes in the boat, I think there's a picture of it here, okay, was not very practical, right? Because there's not a big temperature difference between the cold water and the hot water, so it's not going to turn the turbine very much, okay? Even if you had like boiling water here and cold water here, it's only going to move the turbine a little bit. And how do you keep the water boiling? You have to keep putting energy in, then it's not as viable. Okay, so that was his idea. Never actually built this because it wouldn't work. Okay, but that was the idea, and that was how we came up with the idea for a jet engine. Okay, a jet engine works exactly the same way. At the front of the jet is hot combustion. Okay, burning essentially kerosene, and that's what jet fuel really is. Okay, it's a really hot burning fuel, and when it burns, okay, the energy wants to flow to the cold air that is behind the engine, right? As it goes through there, it turns the turbines, okay, which creates thrust, okay, and pulls air through the engine, okay? When an engine is at idle, okay, when a jet engine is at idle, the turbines have to be turned by electricity. Okay? Otherwise, the heat will go out the front because it's the lower path of resistance. So they have to actually get the turbines turning to start the air going the right way. Once the plane is in motion, it kind of takes care of itself. Okay? But at idle, okay, when you see just an engine or like a jet at the airport and it's just sitting there and the turbines are actually running, okay, they're actually running not off the combustion of the fuel. All right. So we got heat engines and we got heat pumps. Okay, so heat engines, okay, are very simple. You can actually set something like this up with an electric motor. You turn it into a thermocouple. 90 degrees Celsius water in one beaker, 10 degrees Celsius water in another beaker. Okay, energy will flow from hot to cold, and it'll flow through the engine. Okay, and it'll turn the fan. Now, if you put a beaker of hot water and a beaker of cold water right beside each other like this, okay, how long is this going to run for?
Not that long.
Not very long, because it's also just going to go directly across. Okay, energy finds the path of least resistance, and that's way easier than going through the motor. Not that the motor wouldn't run, it will, but it'll only run until the temperature of these two things is the same, and it'll be constantly going slower as that difference changes, just like a battery. Okay, what makes a battery work is the potential difference between the negative and the positive. Okay, as those start to balance, the voltage it produces gets lower and lower. That's actually what we use, okay, on our phones to tell us how much battery power we have left. When it gets to a certain level, there's not going to be enough flow of electrons from one to the other to support what the phone would do. Okay. All right, so those are heat engines, okay, or a thermoelectric converter for this one. Okay, and then heat pumps, okay, heat pumps, like I said, disobey the second law of thermodynamics. but they do it by paying for it. Okay? You have to put energy in to pump the heat out into the hotter area. Right? And that's again what your refrigerator does. So in your refrigerator, okay, there's a compressor, and then there's a whole bunch of these little pipes. Okay? And you can sometimes see them actually on the back of the fridge, okay, or on the bottom of the fridge. And what goes through those is refrigerant. Okay? Refrigerant used to be made of Freon, but now it's made of other things because Freon was bad for the ozone layer. But this stuff goes through here, through the pipes, and the pipes run through the walls and all parts of the refrigerator, and they absorb energy from the inside of the refrigerator. When they absorb that energy, they turn from a liquid to a gas. Okay, so the coolant that's running through is a liquid when it's doing its cooling. So it's absorbing energy from inside. When it absorbs the energy, it turns into a gas. Okay, and then that gas comes back to the compressor. And the compressor, as its name would imply, compresses the gas back into a liquid. When it does that, the energy that it absorbed is now given off, and a fan blows it out into the room. Okay? So the compressor actually gets hot as the refrigerator runs because it's constantly taking the energy from the vapor to turn it back into a gas. Or sorry, to turn it back into a liquid, sorry. Okay, so it takes the gas, turns it back into a liquid, and then pumps the energy that comes from that out into the room. Okay, everybody okay with that idea? Right? That's how your air conditioner works as well, except your air conditioner is outside. Okay, and so the coolant runs through your house, okay, or into certain parts of your house. Air is drawn through there and cooled, and then that cold air is blown into your house, and the heat from the coolant is vented outside. If you've ever stood next to an air conditioner, okay, it's a big fan, and in the middle is this big compressor, right? And so it's constantly putting the heat out, okay? So if you hold your hands over your air conditioner when it's running in the summer, you'll feel the hot air coming out of it, okay? That hot air used to be in your house, okay? It's taking the heat from inside your house and pushing it outside. All right. So I would like you guys to answer those questions right there, but we're going to run out of time. So we'll talk about those on Monday. Okay.
No.